So first of all, this is a pleasure to be among you. This feels like presenting Microsoft to Bill Gates, but like anyway. So uh, f- I chose the title "Formal Verification of Cryptographic Protocols," but it should have been, now that I've seen the previous slides of the presentation before me, it should have been like cryptographers trying to use formal methods. So this, like how I encountered formal verification, was by accident. We were trying to set up like this DNS protocol, and we just stepped into this library because what we mainly do is like try and incorporate new algorithms and see how they fit and their performances. And we kind of tried to tamper with the protocol in a way, but we needed we kind of needed to know if the protocol uh, was safe to use at the end, because like having a perfect algorithm doesn't always mean that the exchange is safe. So about me, ilias Cherkaoui, I'm doing quantum encryption, like both the QKD stuff and the post quantum, which is mainly what I do, post quantum cryptography. And while doing that, sometimes uh, you kind of have to verify the protocols, and you do it formally because I come from a math background, and that is the closest thing to what I can do apart from the networking part and everything. So just to notice, when we get to Proverb slides, I want you to note that like almost everything was taken from the documentation, which is like it should be the reference for everyone that wanted to start using Proverb. So it's like practically Bruno Blanchet and Vincent Cheval documentation. All right. So why do we need formal verification? So sometimes we do implementations, and like I said, the details do matter, because like the attackers, they only like focus on those loopholes, those details. So you cannot ignore some details, you get an attack. You use like an obsolete mode of encryption, like EBC or something, you get an attack. It depends. Like, and also like it allows us to do automatic checking. And if you get like depending on the software you're using, you can handle concurrent or like serial processes, like the case for Proverif, unlike others. Like, yeah, we'll get to that. So the projects that are well known. So you have on one hand Proverif, which is like an automated tool and relying on like the symbolic model. I mean the dollar Viao, when you get like a certain proposition and you can like deduct or like derive something from it and so on. You get the crypto verif, which focuses more on like computational proofs, because like one thing I forgot to mention is like in pro verif, everything like what we assume is like encryption is perfect, so it's perfect primitives. It's like what they call black boxes or something. Like it's you cannot discuss like how safe it is. You have the Tamer improver, which uses heuristic methods, deduction and equational reasoning, and you have FSOR, which uses like SMT and is based on Camel. You have DeepSec, bounded number of sessions. Those are the properties. Cyther uses inference, CertiCrypt, and EasyCrypt, which is like just an improvement of that as far as like timing is concerned. So now let's move on into the pi calculus syntax. So there are people who use lambda calculus, and you may want to delve into that if you were more interested in Haskell programming or something like that. But like since we're going to talk about proverif, pi calculus syntax is the entry to that. And when we get to proverif, it actually uses like applied calculus. So it has built-in functions on top of that. So we have terms for here, like say here, it's the connections are like interconnections, names. Those are the names A, B, C, D, and the processes like for instance here it's the nil process. So you're doing nothing, and you get to output stuff. You get to input stuff. Like say here, like A bar B dot P. So you get to uh, output B on a channel A and then do the process P. So you have in mathematical terms, you have two spaces like two names, and you have like a product with the process P, and you get like the result is like the output is a process. All right, and once you do that, like the channel vanishes, and you're left with the process. You have the input where you're gonna input X in A, and you have parallel, and this will be interesting for people that are doing distributed systems. So you can execute parallel processes. You can do restrictions, is like when the name or like the term is specific to the process, you cannot use it outside of that. It's like bound in a way. Replication, you get an amount of copies, like it's unrestricted, and you also get like the choice for like either that or that. It's like the co-product, like in category theory for processes. And like one example to use that would be communication. So like the thing that I did here, like forget about the implication, just the part on the left, it's like you output B in A, then do the process P, and then B gets transmitted. Like you listen to that on A, and you left, so you're like replacing the term X with B, and the thing on the right is like the notation for that communication. So how does Proverif work? So you get processes that are turned into horn clauses, and then you get the saturation, and then like you verify the lemmas. But like the thing that you input into the Proverif is like the process itself, like the the cryptography, like the process, but like in applied P calculus in the syntax of Proverif. But you also like should have the property that you want to check, like either it's secrecy, authentication, or like an equivalent process or something. So here, like on the command line, you can just type like the thing that you see there, and this is like the first thing that you would see on the documentation of Proverif. So you like declare a free variable, like a free name seed, which is the channel. Here we have the RSA, which is like a bit string, and forget the query attacker. I'm going to explain that, and like you just do the process and you output like RSA on like the channel C, which is public. And here everything on which you don't see private, it means it is already public. So why do we do that? Because we should give the attacker some leverage. We should give him some information. Otherwise, there is no point of doing this verification. And if it's private, he doesn't have that. And this is the output that we get. So at the end, we get like it does the query, not attacker verification. And for here, like it means like in the summary, you get it's false. So the attacker can get his hands on the RSA bit string. So it is true and the name is not derivable by the attacker. All right. It also gives you like an attack trace, and there is like more detail into that. So operations, what can we use? So there are some constructors, like it's like a function, for instance. If you take a shared key encryption, would denote it by like fun and async, and you got like input bit string key, and then you get like the output is a bit string. So it's the basic encryption thing. The destructor, when you're using the rewrite rules, it's like G applied on like the names M1 to Mn. You get like the M. It's like either P or Q. So like the reason we use that, if you see down there, like the fun s-enc. So you have like, when you have an encryption, you use already a constructor, like a way to like retrieve the information from that, the m, like to get back would be to use like a destructors, like doing the decryption. So when you're doing decryption, you use actually destructors. And that, in other words, so if you have like a number of arguments n, and so if you have the clause at, means that the attacker has like, if you give him x1 xn, so the adversary can compute like f on x1, the sequence to xn. Sorry for the typo there. So for instance, for a shared key encryption s-enc, the following clause is generated, the one down there. So for each destructor, if you have that clause, it is generated. The adversary can compute like m when he has like the sequence, the mi, I belongs to 1 to n. All right. So if for a shared key decryption SDEC, like if the adversary has the ciphertext, like say the s-enc and the key, which is supposed to be secret, you can obtain the clear text. All right. So in terms of proverif, say we want to, like, instead of the Needham-Schroeder protocol, I wanted to just talk about like the Denny and Sacco based on like a Bruno Blanchet demo, and say you want to transfer, like you generate a key, which is like a fresh key, K, and A wants to transfer K to B, all right? And to know that it actually transferred that K, he wants to receive some secret from B, which is encrypted in that K. So what he's going to do is like sign K with its own secret, with its own private key, SKA, and it's going to encrypt it with its own public key, PKB. And since it's encrypted in the public key of B, so B has the private key, SKB, and it's going to be able to decrypt that. All right. And it's also going to be able to check the signature. And using that signature, once it checks that, it's going to be able like to know that that's the real key, and get that key, retrieve it, and sign with it another secret, forward it onto B. So if we get to the syntax here, we see a couple of new SK A, new SKB. So we're actually generating like keys, all right, and we're computing like the public ones corresponding to those ones, and we're outputting them on like the public channel, because like we said, like the attacker should have something, all right? So we're doing in, so we're actually listening to the stuff that are coming on the channel C as well, and the XPKB, because we have that in here because like it's not supposed just to be communicated with a certain B. Like give it any public key corresponding to another one, you could be talking to that other one. So what it does is like the thing that I just told you, like it signs with the SKE, encrypts with PKB, and outputs it on C. And on the other end, you have like the B is listening, and once it's listening, at the end it checks, outputs, and the other one receives. All right. So that's about it for the initiation, and I hope that was motivating to get started on Proverif. Thank you.
Yeah, thank you very much, Yes. Anyone has any question or comments, please go ahead. Okay, so while others are thinking, it would have been very nice if you were there, so we could Sam just presented his tutorial on Proverif, so it would have been nice to have you also here with us. Anyway, What do you think is what the challenges that you faced when you were working with Proverif? Were there any specific usability issues that you faced, or can you comment on your experience with Proverif for practical usage? What were the challenges that you faced when you were modeling some protocol, for instance?
Yeah, like I said, my experience with Proverif is like limited to verification of cryptographic protocols, and why I do, like, for me, it is my go-to because like so this is like news to all of you. I'm actually trying with a friend to develop some project similar to PyCalculus, somewhat too formal to like maybe just model certain network protocols, and like because I'm so into like type set theory and like category theory, like that seems the closest. All right, and if that seems the closest, and you're on one hand, you're using algebraic and you're using computational terms, but like once you do the mathematical verification of that, apart from which we all have nowadays, like if you were using a certain algorithm, so once you're finished with that, you want something that is the closest in terms of the logic to kind of verify the protocol as a whole. So for me, like the transition from algebra to PyCalculus to applied PyCalculus to Proverif seems kind of natural, and I love it because like it's unbounded. It's also a responsibility to kind of know how to manipulate like the terms, when to use it, how to use it, and for me, I didn't get like you, you kind of avoid false attacks, so that's a good thing. I had experience with Avispa before, and it's also good, but like for me, Proverb, that's what I use. But like, I'm not saying it's yeah.
Did you happen to have experience with Tamarind also, or was it something that you didn't get into?
Come again?
So did you happen to have any experience with Tamarind, or was this something that you have not yet experienced?
Tamarin, no. Unfortunate, but I did a few basic stuff to be honest, but like nothing as far as like a whole protocol from start to finish. Yeah.
Okay. So any other thoughts or questions? Yes, please.
Uh, how are you using these formal methods for post-quantum crypto algorithms and protocols?
Yeah, that's a good question. I want to I was kind of avoiding that question. Well, the only thing I can say is like I'm working on something like that. How? Uh, well, can you like develop the question more so that like what are you looking for as an answer? Like, what do you mean by how?
Like I was wondering whether you specifically focus on the development of the algorithms themselves, or whether you are looking at protocols that happen to use post-quantum crypto inside. Like, for example, there's work on adding post-quantum crypto to TLS, so you could look at that, or a hybrid version of it. So that's why, since you mentioned at the beginning that you're working on that topic, so I was curious on how the link works with the formal method.
Yeah. To be honest, what I'm doing is like we have a set of infrastructures, and the way we're linking them and using like those protocols, because so far like we're kind of waiting on some some regulations. So the thing that we're trying to do is like not the protocol itself. We're not verifying the protocol itself, but we're verifying how we are doing our own implementation of those post-quantum algorithms within those protocols that are existent in our infrastructure. So like the Alice and Bob like the way we're doing the exchange is actually our own infrastructures, not like the protocol itself. I don't know if that's clear enough for you. I hope that's clear.
Yeah, you're giving a hint.
Yeah. Because like the project I'm working on is kind of confidential. That's why. But yeah, but as a whole, that's it. That's what we're doing.
Right, so thanks a lot. I think that's even if the project is confidential, we can get some things out of it. Like we are collecting the kind of challenges that are related to the verification of problems. So that would be nice to have your input in the evening session. So yeah, cool. Thanks a lot. And